We are almost ready to go in a couple of minutes. So, um, Dr. Basuraj, are you in? Can you unmute yourself and please respond?
Hey, hi.
Hi. And your video too.
Yes, yeah.
That's fantastic.
Just give me 1 second.
You are set to go.
Yeah, go ahead.
Just a second, please. I'm trying to sort this out and in a minute. Yeah. So, welcome everybody. I'm very happy to be introducing Dr. Basuraj from the Department of Chemical Engineering in IIT Madras. Now, it's a small group that's working on droplets and their various properties. And he's one person that I've been interacting with for quite some time, and very happily, I should say so. Today's meeting was intended as a discussion forum where we try and understand what the nuances of droplets are and what it means to be studying them. And we have some experts lined up for today and tomorrow. Of course, we're going to be starting with Dr. Basuraj, then we'll have Dr. Ramkumar from Central University of Tamil Nadu Chemistry. And tomorrow is going to be very interesting in the sense that we have a lineup of how to really analyze the drying patterns in liquid drops, headed by Professor Sujata Tarafdar, and with Drs. Tapti and Mukeshi. And the last would be a couple of talks by my own students on some of our recent work. Just to briefly introduce Dr. Basuraj, he's, like I said, a faculty member in the Department of Chemical Engineering at IIT Madras. He's an MS from IISc, a PhD from KU Leuven in Belgium, and a postdoctoral fellowship from University of Delaware. He concentrates his research on understanding the structure property correlation of complex fluids and fluid interfaces containing colloids, surfactants, polymers and their mixtures, which is an extremely important topic, and especially right now, given the COVID and the amount of emphasis we have on the droplets, aerosols. I think this is one time to start revisiting and understanding the complexities that are involved in this. So without much further ado, I request Dr. Basuraj to take over and make this presentation.
Hey, thank you very much. So I'm just going to share my screen first.
Perfect.
Just, is this okay?
This is okay. Yeah.
Okay. So
presentation mode.
Just I've tried to do that.
Yeah, here at the bottom. Right at the bottom. That's
okay. Hey, thank you for organizing this workshop. So I'm very happy to speak. The topic that I've chosen is to give you an overview of drop evaporation. The way I've structured it is I'm going to assume that people do not know anything in this field, so that I just go from the very basic of this process, and then try and define every term that is kind of used in this literature in this particular field. A drop is a small round spherical or pear-shaped object, okay, or a pear-shaped liquid of small volume that hangs from a surface, or that is adhered to the surface. Okay, that's a definition of a drop. If you look at Wikipedia or one of these sources, this is what the drop is termed as. And we know that drops on surfaces can evaporate if the liquids that form these drops are volatile. Okay, and what really causes the evaporation is a difference in the vapor pressure, P vapor, that is adjacent to the drop surface. So that means, the very close to the drop surface, the vapor pressure is higher compared to the ambient pressure at a distance far away from the surface. Therefore, there's a concentration gradient, and this concentration gradient is what is termed as is a reason for the evaporation of the drop. And in most cases, when you don't have any external influence, what really drives the evaporation is the diffusion of molecules, okay, from the surface into the ambient atmosphere. And now drop evaporation is important in a large number of that we come across, in industry as well as in everyday life. A common example that are kind of listed here is a spray coating, which is an example where you have a liquid solution that is coming from a central nozzle, and then you have a gas stream that is let from the side, and which essentially atomizes the droplets, the liquid that is coming from this channel, and then it converts this this thin fluid element into a large number of droplets, and there's a possibility of moving the substrate and then collect these spray generated droplets on a surface, and eventually these droplets would dry, leaving a thin film of the material on the substrate. The other example is spray drying. There's again schematically represented here. Again, a similar arrangement of atomizer and a gas stream is shown. Again, the droplets are kind of generated because of the atomization process, and there's a chamber where these droplets dry, and once all the fluid is evaporated, you have a fluid that is collected into a container, and the exhaust gas goes up. Okay, and the other examples are inkjet printing, where you have a cartridge containing a fluid of your choice. It could be conducting polymer solution, it could be just the ink that is typically used for printing applications. So in which you have generation of droplets, and these droplets are ultimately deposited on a substrate, and depending upon the spacing between the droplets and the frequency which the droplets come out and their evaporation, you can have some kind of a deposit on the substrate. The other examples where the droplet evaporation becomes important is in agriculture, where you have a nutrient and pesticide delivery. So what you are seeing here is a case where some nutrient that is being sprayed, and it lands onto the surface of the leaves, and eventually the liquid evaporates, leaving out the essential material for the plants to absorb. Okay, so therefore, if you look at all these different droplet processes, we can classify them into two different categories, in fact, three different categories, where you have droplets that reside on a substrate. Examples are inkjet printing, spray coating, and the nutrient pesticide delivery that I've discussed so far. And so you also have contact-free droplets. So for example, those that appear in spray drying, or it could also so happen that the droplets can also evaporate in a combination of the two. That means there could be some part of its lifetime where it is dried in a contact-free mode, and some part of the lifetime it could be drying on a substrate. So what I'm going to do is to take each of these cases and then discuss a little bit about some basic terminologies to begin with, and then discuss about some of our contribution to this particular field. Before I do that, typically when evaporation occurs, of course, the evaporation of pure fluid is also important, both from understanding some chemical engineering principles. But however, if you look at the fluids that are used in printing, coating, or any other process that I discussed so far, they're all multi-component. There is a liquid, and there's also a lot of volatile and non-volatile matter as well, right? So therefore, so what I'm going to do in the remaining time is to consider example where drops contain particles. These are also called as particle laden drops. And so we know that uh, uh, so you can have particles dispersed in a fluid, so that you have a dispersed phase, which is the particles in this case, and a continuous phase, which is the fluid medium in which the particles are dried. Therefore, you have a droplet which contains particles, and these are what are called as particle laden drops, and they occur in a lot of everyday applications as well, right? Um, Now, so more specifically, we're going to look at evaporation of drops which contain colloids and nanoparticles, in which the dispersed phase, that is the solid particles, can be of size range going from 1 nanometer to about a micron, in which case such fluid particle systems are called colloidal dispersions. Or on the other hand, you could have the size range of these particles ranging from 1 nanometer to about 100 nanometer, in which case we term them as what are called as nanoparticle dispersions. Now, one of the interesting feature of fluids which contain such small particles is that they have very high surface area and surface to volume ratio, and they exhibit an interesting phenomena called Brownian motion, which is what you can see from this video, which essentially is the chaotic motion of the particles that is driven by the bombardment of the solvent molecules or the fluid in which they're dispersed, and they kind of move about in a random way. And in such a dispersion, the Brownian force that is acting on the particle is of radius rp is given by the thermal energy, that is kBt, divided by rp. Rp is the characteristic dimension of the particle, and in this case rp is if you have a spherical particles, rp would be the radius of the particle. One of the interesting considerations one has to think about when dealing with evaporation of particle laden drops is the gravity effects. So we know that the particles in a droplet or in any fluid can settle because of the action of gravity, and the settling velocity of these particles goes with the square of the radius, which is the well-known Stokes settling equation. And one should ensure that the particles are small enough that the particle settling does not occur. And the gravitational force Fg that is acting on the particle is given by m times g, and the Brownian force that is given by kBt divided by rp. So one has to ensure that the Brownian forces overweigh the gravitational forces acting on the particle. That can be easily met when we are dealing with small particles. Therefore, the gravity effects which lead to sedimentation of the particles can be avoided. And in fact, most of the dispersions that are of practical importance, they have a really long shelf life. That is because of one of the main reason being that in such dispersions, the gravity effects are negated by one or the other means, and therefore when dealing with drying of particle laden drops, it's important to consider that the effect of gravity is negated. That means the patterns that are going to be generated when such droplets are dried are not governed by gravity, but by the other effects that are going on in the system. Now, the other important consideration is that the particles during the course of evaporation or drying of drops should not cluster or should not aggregate. And therefore, it's again a good practice to work with stable colloidal dispersion, unless one is really specifically interested to look at the effect of aggregation during drying. So therefore, the stable the dispersion can be made stable by using one of the several stabilization mechanisms, most common being what is shown in the schematics A and D, where what is done is that there is a charge group on the particle surface, and this charge group, when it is introduced into a fluid, the particles with such charge group, when they're introduced into a fluid, these charges can dissociate, giving out either a negative charge or a positive charge on the particle surface. And positive or negative charges can also be imparted to the particle surface by dispersing them in different fluids where there's a specific adsorption of ions onto the particle surface. So whenever we talk about a charged particle, there's a concept of electrical double layer that comes into picture. And what you're seeing is a picture of a positively charged particle that is shown by the positive sign that you have on the particle surface. And because of the fact that the system on the whole has to be electrically neutral, you will have negative charges in the solution. And there's a layer of negative charges that is strongly or adsorbed onto the particle surface in a region called stern region, or the stern plane. And therefore, there's a layer of positive charges and there's a layer of counter ions, and that constitutes an electrical double layer. And in the case of charged particles, the charges are typically expressed in units of surface potential. And for all practical purposes, one measures a quantity called a zeta potential, which is the potential at the plane of shear. And this quantity is used to infer about the stability of colloids in a fluid. That means if the zeta potential is very, very high, the particles are stable. If it is 0 or very close to 0, the particles exhibit limited stability. And as we'll go on, I'm going to mention that this zeta potential is one of the important factors that affects the processes that are involved in evaporation of particle Laden fluids. Now, one also has to be aware of what is called as the interactions in a system of charged colloids, and the total potential, which is also called as a DLVO potential, which is the summation of the van der Waals forces, which is always present whenever you're dealing with the molecular system, plus an electrostatic repulsive term, which comes because of the charges on the particle surface. And this van der Waals force and electrostatic force can take different forms. I mean, the expressions are different depending upon the particle geometry that one is dealing with, whether we are dealing with spherical particles in the fluid or whether you have disc-like particles, so on and so forth. And what is plotted here is the potential as a function of separation distance between the particles, and this is the van der Waals attraction term, and the dashed line above 0 is the electrostatic repulsion, and the sum of the two gives you the van der Waals forces. And because of the fact that these two forces are opposing in nature, there's the maxima that comes about, and this maxima tells us something about whether the dispersions in the fluid are stable or not. If the height of this barrier is very, very large, typically several tens of kBt, such colloids exhibit very good stability. The moment the energy barrier becomes of the order of thermal energy kBt, then they do exhibit limited stability. With this background, so we're going to talk about drops that reside on substrate, again to introduce a few terminologies to begin with. Why study these such drops? And it has been shown that this simple problem of drying droplets can be used in several, technologically important applications. I've already mentioned about inkjet printing. When there's inkjet printing, the distribution of the constituents of the drop on the substrate when the fluid evaporates is important, because it is going to kind of influence the quality of the printing that you get. If one is using a conducting ink, for example, whether whether the conductivity is ensured across the entire width of the substrate depends on the quality of the print that you generate. And what you also see an example where this technique has been used in particle separation. What you're looking at is a picture at the top where you have which is the edge of the evaporated drop, and the edge, if you zoom in, you see three distinct colored lines, that is green, red, and blue. And these lines correspond to particles of different sizes. And the reason why they appear different color is because they're fluorescently labeled. And it so happens that if you have a mixture of three different sizes in an evaporating fluid, the smallest particles go to the farthest edge of the drop, followed by the medium size, followed by the largest size. So therefore, one could start with a droplet that contains particles of different sizes, and you can actually separate them into different sizes by using this principle. And the top is an image with model particles, and the second, the image at the bottom is an example where you have a mixture of biologically important particles and molecules, where again a similar concept of size dependent separation has been demonstrated. And the second example that you look in the center is disease diagnostics, where A and C are the images of a person with without any disease condition, and B and D is a case where there is some disease condition. And as you can clearly see, the evaporative patterns that are remaining after the evaporation of the blood plasma are very different, and one kind of uses such simple evaporative patterns as a diagnostic tools in this literature. Again, if you look at literature, you'll see a lot of work where there's discussion of sessile drops and pendant drops, which essentially are that if you have a substrate and if the droplet sits on the top of the surface, then it is called as a sessile drop. And however, if you invert the sessile drop configuration, you get a drop that is hanging from the surface, which is what is called as a pendant drop. And there's a lot of interest looking at both sessile drop as well as pendant drops, and then look at the kind of patterns that are generated after the fluid is evaporated. So whenever you have a drop on a fluid, a drop on a substrate, so you have what is called as a three-phase contact angle, which is the fact that the gas phase, that is in the, if you do experiments under ambient conditions, you have air and you have a liquid of your choice and you have a substrate. All these three fluids meet at a particular location, and this location that I'm indicating now is what is called as a three-phase contact point. And of course, the fact, if you take a hemispherical cap, okay, there's a continuous line across which the three phases meet. That is what is called a three-phase contact line. And one could draw a tangent to the drop surface at the three-phase contact line to obtain a parameter called three-phase contact angle, which is related to the interfacial tension of the liquid, the interfacial tension of the solid, and the interfacial tension of the solid liquid interface through what is called as a Young's equation. And the contact angle theta can be different depending upon what kind of substrate one is dealing with. You could have a substrate where the contact angle is greater than 90. You could have a case where the contact angle is less than 90. So when the contact angle is greater than 90, you typically term these surfaces as hydrophobic surfaces. However, when the contact angle is less than 90, you think about what are called as hydrophilic substrates. And when the contact angle is exactly 90, they are what are called as neutrally wetting substrates. And the reason why the substrate wettability is important is because they affect both the evaporation process, both in terms of the kind of deposits that are going to form after the fluid is evaporated, as well as the lifetime of the droplet is also affected by what is the contact angle of the fluid on the drop. So you'll often again come across some terms called constant contact radius drying mode and the constant contact angle drying mode, which essentially are that if you have a substrate and if you have a droplet, if you monitor how the radius of the contact line, I mentioned that the moment you have a hemispherical cap or a spherical cap on a droplet surface, the contact line is going to be a circle, and I can monitor what is the radius of the contact line. If the radius of the contact line remains constant during the course of drying, which happens in the case of what are called as pinned drops, that means the pinning ensures that the contact radius remains constant during the drying period, and accordingly there's a decrease in the contact angle with time, and such a mode of drying is what is called as a constant contact radius mode of drying. On the other hand, you could have a case where the contact radius decreases with time, which is what is depicted in the figure here. The dashed line is are the profile of the drop when the evaporation has proceeded to some certain extent, and in such a case, the radius of the drop decreases with time, and the contact angle continues to remain constant, which is what is called as a constant contact mode of drying. So with this background, so I'm just going to show you some videos of what could happen when a drop would dry. So this is a video that is taken from the top. So what you're looking at is a fluid containing particles. Yeah. So what you should notice is that you know, there is a formation of a thick deposit at the edge. Maybe I'll just okay. There's a formation of a looks like the video. There is an issue with the video. Maybe the next one is going to be more clear, hopefully. So this is a more zoomed in version wherein we are looking at the edge of the droplet, that's here, and you will see that the particles are coming and depositing at the edge. So these were the particles that were initially dispersed, well dispersed in the fluid, and as the evaporation proceeds, the particles come to the edge and then keep on depositing there. Okay, so this is a very common phenomena that you will also observe when there is what is called as a coffee spills. When you accidentally spill a drop of coffee on surfaces, you can notice in this particular image, which I've taken from Wikipedia, is that the edge of the drop appears more darker compared to the interior region, and the fact that the coffee coffee particles are reddish brown in color, one could imagine that these deposits have formed because of the deposition of particles at the contact line. So therefore, so in droplets that dry on a surface, the evaporation leads to a deposition of particles at the edge, and this process is what is called as a coffee ring effect or a coffee stain. And again, as I mentioned, the name comes because of the fact that such kind of deposits are observed when there are coffee spills. Okay, yeah, so now when the sessile drops are evaporating, so this coffee ring that I mentioned about, so these form only under certain conditions. That means certain conditions have to be met for the formation of such coffee ring deposits. One is that the solvent must evaporate. That means the fluid in which the particles must evaporate, and typically drying drop experiments are conducted with aqueous dispersions, and the fact that the water evaporates under ambient conditions, the first condition is met. Um, and the second condition is that the substrate, the fluid should make a non-zero contact angle. That means if you have a very thin film of fluid which completely wets the surface, then the coffee rings are not going to form. Therefore, it should form a droplet with a finite contact angle, and the contact line should be pinned. Again, I kind of mentioned this in the previous slides, where the fact that there are some heterogeneities on the surface, nanoscale heterogeneities, which are inherent to the particle, which are inherent to the excuse me, which are inherent to the glass substrate or any substrate that one deals with. The pinning is ensured, and of course, when you have when you don't have any pinning, this coffee ring are not expected to form. Excuse me. Now, the reason for the formation of this coffee ring deposits has been attributed to what is called as a non-uniform evaporative flux. One could derive an expression for the evaporative flux that is occurring from the droplet surface, and it turns out that it goes as 1 over r minus r to the power of lambda, where lambda depends on the contact angle, the instantaneous contact angle of the fluid drop, and r is the radius of the drop, and small r is any radial location from the center. And if you take a typical example of lambda is equal to 1, J of r is proportional to 1 over r minus capital R. If you substitute small r is equal to capital R, that is at the edge, it turns out that the flux is infinite. And if you take an example where r is equal to 0, that is in the center, small r is equal to 0, that is in the center, then J of r is proportional to 1 over r. Therefore, you can imagine that the evaporative flux at the center of the drop is less, okay, and it increases as you go away from the surface, and it is maximum at the drop edge, okay. So therefore, there is, in essence, there is more evaporative flux from the edge, and the fact that the contact line has to be pinned, okay, even though there is a higher evaporation of fluid from the drop surface, it induces a fluid flow from the interior towards the droplet edge. And this fluid flow, essentially what it does is it carries the particles that are dispersed in the fluid, and it kind of deposits the particles at the edge, okay. Therefore, there's a particle transport which is mediated by the capillary flow that is arising because of the fact that the fluid that is evaporated at the drop edge has to be replaced by the fluid in the interior to ensure that the contact line is pinned during the evaporation process. Therefore, the mechanism of formation of coffee ring is fairly well understood, and it is known that this capillary flow is what leads to the deposition of particles at the edge. Okay, so with that background, so I will come to talk about some recent contribution that we have done to this field. So I'm going to hopefully discuss about two cases. One is we are going to look at drying of drops containing ellipsoids, which is work done by Venkat, who is now a faculty at IISER Bhopal, and the effect of orientation of the drop on the on the deposit patterns, which is the work done by Ranjit, Shivani, and I've done this work in collaboration with Sumesh, who is a faculty at IIT Madras Chemical Engineering. And the funding sources are DST, a lot of support from IIT Madras in terms of various types of grants. Okay, so we one thing to keep in mind is that the evaporation of the sessile drops gives coffee ring deposits, and with this background, we look at drops that contain several types of particles, that is particles of different aspect ratios. We've been able to make particles that have different aspect ratios, almost spherical, what you see in A, and B, C, D show elliptical particles of different aspect ratio. And one thing to notice is that these particles are very, very small. The length of the particle is, about 100 to 200 nanometers, and the diameter of the particle again varies from about 29 nanometer to about 105, and therefore the ratio of the length to diameter gives you aspect ratio, and the aspect ratio varies from about 1 to 6. Typically, evaporation experiments are carried out with very small amount of particles in the fluid. So we are considering volume fraction of the order of 10 power minus 3, volume fraction defined as the volume of particles in the fluid divided by the total volume of the fluid. Now, one of the nice things about, so we have chosen hematite particles in these experiments because their aspect ratio can be tuned. Other important aspect of working with these iron oxide particles is that I can tune the surface charge on the particle from positive to negative, depending upon the pH in which the particles are dispersed. So you can have particles positively charged, that is positive zeta potential, when the pH is about less than 9, and when the pH is more than 9, they're negatively charged. And these experiments are done on a substrate which is silica, and the silica has a surface which is predominantly negatively charged throughout the pH window that we are trying to look at. So I talked about colloidal interactions. So in a evaporating drop problem, one has to account for both the particle-particle interaction as well as the particle-substrate interactions. And because we are dealing with charged particles, we'll have DLVO interactions for the both. That means we will take the contribution of van der Waals forces and electrostatic forces both for the particle-particle system and the particle-substrate system. And what you're looking at is a plot of the particle-particle interaction scaled with thermal energy for different pH ranges from 2 to 12, and again particle-substrate interactions from pH 2 to 12. Okay, what is important to notice in these plots is that there's a pH window where you will see that the interaction potential is, the overall interaction potential is negative. For example, for pH 6.5 and pH 6 and pH 8, okay, you will see that the interaction potential is negative. That means under these conditions, the particle-particle interactions are attractive. However, if you take the pH 12 and pH 11, or for that matter pH 2, you will see that the overall interaction potential in certain distance range is negative. That means, sorry, positive. That means there's a overall the interactions are repulsive. Okay, so and a similar case also for the particle substrate interaction as well. So the point that I want to make is that it is possible to tune both the particle-particle and the particle substrate interactions by choosing a combination of particle substrate and the pH. And as I'll show, this will have some important consequences on the deposit formation. So this is the overview of the result. So what you're looking at is the deposits that form at pH 2 and pH 6.5, and they are classic coffee rings. That means there's a deposition of particles at the edge of the dried drop, both for pH 2 and pH 3. However, if you take pH 6.5 and pH 8, so you see that there's a more uniform deposition of particles throughout the deposit. Okay, so that means where if I take the case corresponding to pH 2 and pH 3, okay, when the particles are highly charged, we seem to be getting a coffee ring. And if you take a case where the particles are weakly charged and the substrate is reasonably charged, so we seem to getting a coffee ring suppression. Okay, so the way we understand these results is that if you look at the zeta potential plot at pH 2 and pH 3, the substrate is weakly charged. Okay, so that's what was evident. Now, and of course you have particles that are positively charged under these conditions, and even though the substrate is weakly charged, there could be electrostatic attraction that leads to initial deposition of particles on the substrate. However, so once this is done, there are a lot of free particles that are available in the bulk, and these bulk particles are carried towards the edge, leaving out a coffee ring deposit. Okay, because the particle concentration is considerably higher, that there could be some deposition of particles on the substrate, maybe a monolayer. But once this layer is formed, there's a repulsion between the ellipsoidal particles, and that leads to free particles in the fluid, and these free particles are what free or the non-aggregated particles in the bulk, which are what are carried to the edge because of the capillary flow or the evaporative flows. Now, if you have a case where the particles are weakly charged and the substrate is highly charged, then there's a deposition of more and more layers of particles on the substrate, and therefore you don't have any free particles left in the fluid, and therefore even though there's capillary flow, the particles are stuck to the substrate, and therefore there's no deposition of particles at the edge. So therefore a strong particle substrate attraction is what leads to the uniform deposition of colloids in this case. Now, so what one could do is I can negate the particle substrate attraction. That means I can make, if I make the substrate hydrophobic, then I can get rid of the substrate particle interactions. So in such a case, we again recover the coffee ring deposit, in spite of the fact that these the experiments are done at pH 6.5. So if you compare the pH 6.5 case here and the pH 6.5 case here, in the second case, you have a coffee ring formation. That's because we've been able to suppress the coffee ring effect. We've been able to enhance the coffee ring effect because of the fact that the particle substrate interaction is suppressed in this case. Okay, so with this in this works, I would like to conclude that we get coffee ring deposits at the conditions where the particles are highly charged, irrespective of the aspect ratio, and when the particles are weakly charged, the particle substrate attraction leads to uniform deposition of particles, again irrespective of the aspect ratio that we have looked at. So therefore, the DLVO interactions is what control whether there's a uniform deposition of particles or the formation of coffee ring. I would quickly like to discuss about some recent work that we have done, in which we have looked at the effect of orientation of the substrate. It turns out that in several applications, be it spray drying or coating applications, or in applications where you spray nutrients on leaves, the orientation of the substrate need not be sessile in all the cases. You can have substrates of any orbit orientation, and moreover, the wettability of the substrate can be different. Typically, if you look at leaf, most of the leaves are hydrophobic, right? So therefore, so one would also be interested to look at, drying drops at different orientations. So some of the recent work that we have done, we have shown that it turns out that under certain conditions, the sessile drops, although they give coffee ring effect, where the deposition of particles at the edge. So if you dry the same drop in the pendant configuration, we see accumulation of more particles in the center, what is called as a central dome formation. And if you dry particles in a vertical droplet in a vertical configuration, it turns out that more and more particles deposit at the advancing side of the droplet. So now because we work with very small particles, the gravity effects are not important. Therefore, we know that these different deposits that we see here is not because of the gravity induced settling of the particles. It is because of the gravity induced deformation of the droplet. Okay. These are some microscopy images of the drops dried in sessile, pendant, and vertical configuration, and different substrate wettabilities. Theta is equal to 12 all the way up to 120. And you can see that, most of the studies to date have been done with, even when they have done different configurations, the experiments are done with hydrophilic substrates where the contact angle is very low. In such cases, you don't find subtle differences in the deposit patterns. However, when you look at the effect of contact angle, you can clearly see that the deposit patterns are very, very different. That means if you take contact angle of 90, you get coffee ring in sessile mode, central dome in the pendant drop mode, and a deposition of the advancing side in the case of vertical drops. So we have kind of done experiments to quantify the spatial distribution of particles in the deposit. This is the intensity profile, which shows that there's a more deposition of particles at the edge, in the center in the case of pendant drops, and the intensity of that deposit increases with increase in the wettability. And however, in the sessile drop, the peaks in this black curve shows that there's a coffee ring formation because of the accumulation of more particles at the edge, irrespective of the particle wettability. So we have kind of done a more detailed study of this phenomena, and it turns out that the total evaporation time, that is the time that the drop takes to, the time that the fluid in the drop takes to completely evaporate, it also depends on the orientation and also the wettability. If the substrates become less wetting, that means when the contact angle is say 120 in this particular case, you see that it takes a much longer time to evaporate. And if you look at the sessile and the pendant drop mode, the total evaporation time is lower. So this evaporation time also influences the nature of the deposit form. So in the interest of time, I'm just going to quickly mention that the reason why we get different deposit patterns is because of the induced deformation of the drop. Okay, so what you see is a plot of the bond, how the drop shape varies as a function of bond number. Bond number essentially tells us something about whether the drops are deformed in the presence of gravity or not. If you have a small bond number, the surface tension forces are dominant, the drop remains to be spherical or a spherical cap. However, if the bond number becomes higher, the drop shape is deformed, right? And this deformation of the drop leads to what is called as a drop deformation mediated processes. That means the particles can adsorb to the interface, and they can move along the interface, either deposit at the edge, or they can move along the interface and then deposit at the center, depending upon the curvature of the drop. Okay, and for this, the adsorption of the particle at the interface is important, and that is known to occur because the interface anyway recedes during evaporation, and this receding interface captures some particles, and once the particles are at the interface, they can move along the interface as well, leading to the coffee ring formation or the central dome deposit formation. And this occurs independent of the drop volume. Um, so you've looked at the effect of drop volume here. So this is a sessile case and the vertical case and a pendant drop case. You will see that the intensity of the central deposit increases with the increase in the drop volume. Again, shows that the gravity effect becomes important when you have larger droplets. And we have also shown that this also occurs independent of the particle shape as well. So with this in mind, so we have been able to show that there's a coffee ring formation when you have drops dried in the sessile mode. There's a coffee eye or asymmetric deposit formation when the drops are dried in other orientation. So in the next 10 minutes or so, I'll talk a little bit about drying of contact feed drops, which occurs, for example, in spray drying. Again, spray drying is a very important scalable process that is used a lot in food industry, agricultural, and pharmaceutical formulations as well. And this is an example of the formation of milk powder by spray drying of milk, protein particles, and drug-loaded particles, which I've taken from literature. This is a technique again used for making particles of very different morphology, depending upon the kind of particles that you deal with, the kind of conditions that you maintain during evaporation. And one of our recent contribution in this field is that we have done experiments where we have spray dried particles, droplets with particles of different aspect ratios. This is the left side are the images where the droplets contain smaller aspect ratio ellipsoids. Excuse me. On the right, where the droplets that are being dried have a higher aspect ratio ellipsoids, and it turns out that depending upon the aspect ratio of the particles, so you either get a more spherical granules, or granules that are deformed, or the granules that are in the shape of a donut, depending upon the aspect ratio of the particles in the fluid. So if you're interested to know more about this, so you can drop me an email. So I'll be happy to discuss this a little bit. Now,
I think there is a small problem. We seem to have lost Dr. Basuraj's connection. Dr. Basuraj, are you around? Okay, we seem to have lost him. Let's give him a couple of minutes to come. But in the meanwhile, if any one of you has questions, maybe you can ask. Oh, you're back. You have to unmute. Dr. Basuraj, you need to unmute. Yeah.
Yeah, I've done that.
That's good. Yeah.
Can you just tell me where you lost me?
Just the last 30 seconds or a minute. So the last slide,
okay.
Essentially. Not much.
Okay. So yeah. So I was going to say that. So we've looked at examples where the drops dry on substrates. We have also looked at cases where the drops dry on in non-contact mode. That is the drops that are dispersed in the fluid, and drying of such particle laden drops occur. And what is also of interest is the case where drops could either dry in by the case A, B, or a combination of the two. And an example where all the three modes of evaporation could be present is the case of current pandemic, that is COVID-19, in which the transmission of the disease, as all of us know, occurs because of the respiratory droplets, which are the drops that are released during cough, sneeze, or talk.
Can I just interrupt you for a second? Could
Yeah.
you share your screen once more, because some of us are seeing a blank screen.
Oh, is that so? Okay.
You're sharing.
Okay.
I'm sorry about this, but
Is it okay now? Is
wonderful.
it
Wonderful. It's good.
Okay. So I was just going to say, I was just trying to wind up my talk, just to talk a little bit about the importance of drying problem, in which there's a lot of interest in the recent times to look at drying of respiratory drops, which are the drops that are released during cough, sneeze, or talk. And as you can imagine, see, such drops that are released can either dry, when they're dispersed in air, like as aerosols, okay, or they could be deposited on the substrate, and it could also so happen that for a part of their existence they could dry in air, and then they could continue to dry when they're deposited on the solid substrate. And of course, we have also talked. There's been a lot of interest looking at the time that these drops take for evaporation, and such droplets are very complex, right? I mean, because of the fact they're much smaller drops. If you look at drying experiments done in the laboratory, where you use micropipettes for dispensing droplets, typically people work with droplets that are few microliters, in which essentially leave droplets that are that take a contact diameter of a few millimeters. On the contrary, the respiratory drops are much smaller, and they are multi-component. There are more than one component present in the fluid, and the concentration of there could be virus particles depending upon the disease condition as well, and the concentration of these virus could also vary depending upon whether the infection is in an early stage or an advanced stage. Again, these drops are inhomogeneous. So when we talk about model colloids, the particles are very well dispersed in the fluid. However, in the respiratory droplets, you could have some regions where the viscosity could be low, some regions where the virus concentration could be higher. Moreover, they're highly viscous. There's both volatile and non-volatile constituents in these droplets. And of course, wettability of the substrate, which dictates the lifetime of the drops as well, is also important as well, right? So therefore, I think some of the work that we are designing now would be to look at some examples of this sort, where we would like to kind of prepare model fluids of these respiratory fluids, and then look at their drying patterns. So with that in mind, I would like to end my talk, and I would be very happy to answer any questions. Yeah, thank you.
Thank you very much, Dr. Basiraj, for that. That was a very, very interesting and very succinct introduction to drops. I have a few questions that I've collected from both the YouTube and from here. Srinivasa Varadarajan, somebody that I know, asked, I was wondering if the particles can directly escape into the gas phase during an evaporation phase.
I doubt that could happen, because I mean, see, first of all, the reason why the fluid also evaporates is because of the latent heat as well, right? So therefore, I mean, unless you kind of perturb them externally, it could so happen that maybe I may have a fluid with particles, and if I can drive these particles by external field, like so it could be magnetic cords or some external field, then that could be used to drive the particles out of the drop. But in normal cases, uh, I'm kind of confident that the droplets would not, the particles, these are nanoparticles or colloidal particles dispersed in the fluid, will not escape the drop during drying. What escapes is only the solvent molecules or the fluid molecules in the drop.
Okay. I guess that answers to a certain extent. Dr. Kanmani says, very nice presentation. My question is, how can this principle be used for the movement of mucus? Can it be stopped by increase or decrease of surface tension, viscosity, etc.? And this is being asked mainly from a societal application in the broader sense. I think it's basically to do with COVID and,
Yeah. So when you say movement of mucus, so I assume that I'm going to assume that this question is about stopping the movement of mucus on the substrate. And then I'm going to answer this question. So the movement of mucus on the substrate, I mean, we talked about pinning, and right. So pinning essentially ensures that the droplet is stuck onto the particle surface, right? So all of us know this well-known example of lotus leaf effect, right? So in which say water drop that falls on a substrate, it just rolls off, right? It collects all the dust and then rolls off. That's not a good substrate, in the context of COVID now. That it'll be, of course, the pinning of the fluid could occur if there are some heterogeneities on the particles, the droplets, on the substrate. So typically, the mobility of the mucus on the substrate can be minimized if, for some reason, the surfaces are made rough, such that the droplet is pinned to the surface for a longer duration of time. Therefore, their mobility is restricted.
There is one question from Otashi, who's one of our panelists and the speaker tomorrow. She says, I think this was with reference to your previous answer, but salt molecules, which is her area of expertise, like H2SO4 salt, can grow outside of a droplet.
Okay.
Otashi, do you want to come in?
Yeah. So maybe before I can just add a quick point. So when see, I was discussing about these nanoparticles and the colloids, right? I mean, see, for such dispersed phases, escaping from the fluid drop during evaporation is very unlikely. But if you look at the molecular systems, when it could so happen that they could also leave the drop as well during evaporation. So my answer was more specific to the case where the dispersed particles are the nano or nanometer sized or micron sized particles. However, when we talk about the salt, right, the size is very comparable to the molecules of the fluid itself. I think in such cases, the evaporation, they could leave the surface, of course, if sufficient energy is given for them to escape.
Okay. This is a question from Shabnam Beg on the YouTube. The question is, as I understand what has been typed, is the rate of evaporation similar for all solutions?
No, the rate of evaporation is controlled by, I didn't talk about this aspect. The rate of evaporation is controlled by a lot of factors. Number one, the contact angle of the fluid drop on the surface. That means if the contact angle is low, when the fluid drop spreads, there's more surface area available for evaporation, so it will evaporate quickly. Unlike if you take a case, for example, say neutrally wetting, where the drop takes the shape of a perfect half sphere, okay, that will take a little longer time to evaporate. It depends on the humidity conditions. It depends on the temperature of the surrounding. It depends on the temperature at which the substrates are kept. Okay, but if the fluid that one is working with is the same. For example, if one deals with water as a fluid medium, and if I take 1% silica particles in the fluid versus 1% polystyrene particles in the fluid, given all other conditions being same, the total time of evaporation for these two cases should be same. But however, if one maintains different ambient conditions and different heating and other stuff, it will definitely be different.
We have a series of questions coming in, but for the want of time, I will ask you one more question and maybe one person who wants to speak to you directly. The last question that I will be asking on behalf of the audience is Gayatri Patar, who asks if what is the lifespan of COVID-19 on surfaces and on different materials?
So, I mean, see, there are, I mean, I was listening to a talk by a doctor and in
Hello?
the lifespan could be, hello? Yes, ma'am?
Please, please. Go ahead, Dr. Basaraj. There's some problem here.
Yeah, so I was just saying that, you know, the life. See, typically when we do drying experiments in the lab, you know, a microliter drop takes about 8 minutes for drying. Okay, typically water drop, maybe at 25 degrees centigrade, 50% humidity, you know, something like that. But now that is for pure water drops. But however, as I said, I think the respiratory droplets are more complex, you know, and it has been known that the evaporation in the lifetime of such drops could be few hours to even few days as well, right? Depending upon what substrate, they're deposited on. So therefore, I think it's there have been some studies on the evaporation time of such droplets. So maybe I can point to some literature along those lines. But the homogeneous fluid that we deal with, they typically take about a few tenths of minutes.
Okay. Dr. Kamani wants to ask you something, and I'll request you to make it short.
Sir, good morning.
Hey, hi, good morning.
Sir, my question is directly to the application of the COVID environment. Your study is very nice, sir. But my main question is how to prepare the PPE kit and the instrumental operations in COVID environment. We have to prepare a liquid or you take without, there is no medicine still now, but you prepare a liquid such that the surface tension and viscosity which should vary, and we should have to collect the COVID viruses at a particular point and kill. My aim is to, it should not adhere to the surface for longer time, and we should have to collect it and we have to kill it. It is my question, sir. How it is possible?
No, I think, I mean, see, instead of going for collecting, right? I mean, I think the reason why there's been a lot of emphasis on cleaning surfaces frequently, all that is essentially to kill it, right? I mean, you don't really have to collect it. You know, all that you would have to do is ensure that there is a sufficient, regular cleaning either of the floors or the surfaces that you typically touch. And, so yeah, I mean, IPA solution, right? If you take some alcohol solution, like say a hand rub or a sanitizer, that's good enough. 10 seconds, just wipe it up, it just goes. I think, yeah. So in terms of killing them, I don't worry. But I think the major challenge that I think in the context of COVID is that how do we simulate droplets that are very that capture all the characteristics of a respiratory drop. I think that's a more challenging thing at this point, especially if I really want to do a fundamental study of understanding these deposits formation and all of this. Okay, so I think that's something that me and some of our colleagues have been discussing about, and we're going to think a little bit along those lines in the next few weeks.
Thank you, Dr. Baswar. I mean, now there are plenty of questions, but I think I need to let the next speaker also take over. So,
okay,
Khan, thank you enough for having agreed to spend time with us. Because I think with the COVID-19, this has become a very, I mean, suddenly there is a lot of interest in drops and droplets.
True. Yeah. Thanks so much for everything. Yeah, it was
thank you
thanks for hosting. Yeah. Bye.
Our next speaker is Dr. Ram Kumar, who is my colleague from the Department of Chemistry at CUTN, and he's also my research collaborator in self-assembly of liquid drops over polymeric surfaces. Dr. Ram Kumar got his PhD from IISc Bangalore, working under Professor Ramakrishnan, and then after which he did a postdoc at Wuppertal University in Germany, and he's been with us. Well, without much further ado, Ram, take over. Unmute yourself, please. Yes.
Okay. Good morning, everyone, and I thank Dr. Madhurima for giving this opportunity. Let me start the presentation. Screen.
Can you share your screen? Yeah.
Is it in presentation mode or?
Presentation mode, please. Up.
Is it okay?
Up left. No, it's not yet gone into presentation. Yes. Thank you.
Okay.
It's yours. The screen is yours.
Good morning, everyone. Today I am going to present you on how do you manipulate the thin film after you make a thin film using a polymer and using the condensation of water droplets onto the surface. So I understood that the detailed discussion has been done in the last 1 hour or so on the evaporation of the liquid droplets and the coffee ring effect and so on. It's a very nice talk, and it gives a very good background to proceed further from here on. I have made the presentation with the following scheme, where I will slowly give an introductory note on thin films. Then I will move on to polymeric thin films. The polymeric thin films, from there we move on to breadth figure. The breadth figure was research on breadth figure started before the work on polymeric thin film. However, slowly it caught up with polymeric thin film. Then from there, how the organization of this water condensate into a hexagonal pattern give rise to honeycomb patterns due to the breadth figures. And I'll summarize and I'll give some examples which are very fascinating, what kind of morphologies and structures you can get onto the thin films and so on. To begin with, we are all used to interact with many of the thin films in day-to-day life, such as a glazed part or the mirror and so on. One of the very oldest thin film known to the mankind is on the glazed work, especially on brickworks and pottery, which is excavated, especially in the around 800 to 900 BC period. So the purpose of making glazing is to bring in change from the bulk material, or to bring in aesthetic appearance. We don't know why it happened in the 800 BC period, but now we know that we would like to modify the surface by having thin film onto the bulk material. Okay. The importance of thin film in a different context was explored in the 17th century or the late 16th century by Newton, Hooke and others. And we have done several experiments during our school days using this Newton rings. Where we try to
I'm sorry, could you be a little closer to the mic, please, so that you're louder?
Okay. So what we have done experiments during our school days is to understand the thin film of air trapped between large convex lens and flat surface. So thin films is known to us in different ways. In what way a particular coat attains the property of thin film? Is it a few micron thickness gives the categorization as a thin film, or is the property that gives is a serious question. And since there is no clear definition on the thickness below which a film become or takes the characteristics of a thin film, is because of the following reason. The primary reason is different properties scale differently with thickness. For example, optical thin films, which usually in the range of 400 nanometers, comes under the category of thin film, while when you study the electrical property, 50 nanometer thickness is sufficient enough to bring in the change in property. So a thin film with respect to optical properties is of 400 nanometer range, whereas a thin film with respect to electrical properties of 50 nanometer range. So there is no clear cutoff limit for the, what is it called, the thin film thickness domain. So typically a thin film ranges to few micron thickness, but depending upon the final application and utility, we can categorize a thin film. And before going into the polymeric thin film, how do you make a thin film? Considering one aspect that I am having a very solid substrate, the substrate is rigid and also solid. So I have two options. One is to go via gaseous state, or otherwise to go via solution state. In the case of gaseous state, physical vapor deposition, ion beam assisted deposition, or chemical vapor deposition are the techniques, and some more techniques are there where you do sputtering to remove the coat and create a thin film and so on. So the gaseous state involves working under a slightly higher temperature. The gaseous state involves working under very clean environment, which is require a stringent environment and so on, compared to the liquid state or a solution state. When you come to liquid state, you can directly melt and do the coating, surface welding, for example, or thermal spraying, or you can do something called laser assisted coating using at high temperature. All these involves slightly higher temperature. This requires the substrate to withstand that high temperature. So that's the one confinement when you work on this gaseous state and molten state, is the substrate should be robust enough to withstand this high stringent environment. To circumvent this problem, other approaches involve solution state, wherein you go for sol-gel techniques or electrochemical deposition, or you can go for a direct solution deposition. So now I will switch gears and focus only on making this polymer thin films. And for those audience who are not very familiar with polymers are comparatively large molecules. Most often we work with small molecules in organic chemistry, but polymers are comparatively large molecules. And because of their significantly large dimension, many of the physical properties have slightly different behavior compared to small molecules. It gives elasticity, it gives rigidity, it gives stretchability, and there is a different viscosity. When you take a single polymer, and the single polymer itself will take a very large dimension of let's say nanometers and so on. So there is a completely different domain compared to a small molecule and polymer. So considering this, you can make a thin film coating. It depends on the nature of the polymer. One of the simplest approach is to do something called a dip coating, where you take or you hang in the substrate that is to be coated onto or inside a container which is having a solution, and there is a rate at which you pull off the what is it called, the substrate away from the solution. And due to that pulling off, what you do is you allow the solution solvent to evaporate, and then a thin film of this polymer is coated. And during this process, And various important parameters to be controlled are considered is the rate of cooling, the concentration of the polymer in the solution, and the interaction between the solvent, the solution, the polymer, and the substrate. So we have, over the period of years, expertise on doing this kind of uniform coating using dip coating technology. Another even more simplest approach is the drop casting approach. And in the last talk, we spent more time on understanding the coffee ring effect and other movements of particles due to the evaporation of the drop casted solution. So what happens in the drop casting solution, if you are not able to maintain the viscosity of the solution evenly, there is a possibility to generate an uneven film. Either it can form a coffee ring effect while drying, or it can have a what is it called, both coffee ring and also concentrated deposition at the center of the drop. So this problem is due to the differential evaporation rates at the edges compared to the center of the drop. And since the solvent has a tendency, or the solution has a tendency to resist concentration thermodynamically, the solvent moves very close, at a faster rate towards the edges if the evaporation is faster at the edges compared to the center. And due to that, it carries also the dissolved whatever solute along with it, and then it slowly deposits over the ring. This is how we get some kind of a deposition as a coffee ring. Moving to the next approach is to do something called a spin coating, and the spin coating is more or less what we call most preferred method in laboratory scale. For one particular reason is it gives uniform film thickness over the surface on which you do the spin coating. Here the parameters that should be carefully controlled is the rate at which you do the spinning, the time for about you do the spinning, the concentration of the solution you use, the interaction between the solvent and the substrate. You can have a hydrophobic or hydrophilic substrate. Suppose if you have a hydrophobic substrate and try to coat with a hydrophilic solution, then nothing will stick onto the coat, and vice versa. So you have to play with the surface and the solvent system to get uniform coating. One problem that may arise due to spin coating is if the polymer is anisotropic, or if you have two different functional handles in the polymer, there is a possibility for the polymer to stretch and align from the center to the radial, and you have a radially distributed systems in case of spin coated materials. Slightly complex method is the Langmuir-Blodgett deposition method, where you try to make a monolayer of the let's say amphiphilic molecule in two different what is called at an interface with the two different liquids of different polarity. Usually liquid chosen is water, and then you will have air, and the amphiphilic molecules try to align in such way that the hydrophilic part tend to be exposed towards the atmosphere, air, hydrophobic, while the hydrophilic part tend to be in the proximity to the liquid surface, generally water. And then you slowly pull the move the barrier, generate the whatever single film, and then move the substrate from the middle, and then you have a single layer of this amphiphile coated onto the as a Langmuir-Blodgett deposition method. The last but not the least method is the spray coating, which is economically scalable method compared to other methods, where you do a spray. Here also the nozzle's diameter, the rate at which you are spraying, the rate at which you are moving from surface 1 to surface 2, and the rate at which the solvent evaporates because of the thermal conditions you keep. So which is thoroughly discussed in the previous session itself. Spray drying is another technique where you try to get the coating of this solution, especially polymer. Besides other techniques which I have not mentioned here, is you can also make painting directly, which will not give as uniform coating like this, but however it is, in some instances we use painting using a brush or some other aid which is used to make a thin film. The film thickness is not uniform in those methods, and it's very ununiform as well. The thickness cannot be controlled. There are many difficulties with this direct painting method. Other method involves usage of what is called screen printing technology, where you can do the coating onto the substrate using screen printing. Here also the thickness cannot be controlled or cannot be lower than a certain limit. Usually it is of more than 100 microns in the case of screen printing and related process. So now we know that we have prepared or we know how to make a thin film. There are various approaches. One can choose the method to make a thin film depending upon their own objective and the nature of the solute, nature of the substrate, at what conditions, the dimension of the substrate, and so on. So once you make the thin film, whether the thin film is going to be a smooth film or whether the film is the final product or not, is the intriguing questions for last few decades. And people have come up with a very nice, interesting approach to modify the surface. So to transform a thin film into fascinating patterns, which we'll discuss in the next few minutes. Before going into that, I would like to recollect some of the fundamental ideas that you already have in, I have learned earlier, is the breadth figure. The word breadth figure comes from the observation of the phenomena when you breathe very close to the surface of a glass in a cold, humid atmospheric conditions, you generate condensation of droplets onto the surface of the glass. It's not necessarily a glass, it can be of any surface, but only thing is the surface has to be very cold, and since you breathe, it automatically contains high concentration of moisture, high humidity is there, and that generates something called condensation of these droplets onto the surface. This was thoroughly investigated at the beginning by Sir Rayleigh, Lord Rayleigh, and his interest was to know the condensation of water droplets onto clean glass surface, where he used this change in the optical density, measuring the optical density as a function of this condensation. The subsequent work carried out by Bartel and Rouge focused on one conclusion, that breadth figures on a cold surface, depending upon the wetting properties of the surface, can be condensed to form a uniform film which appears dark in an optical microscope, where they try to do the measurement at a very close, low angle. And also the other possibility is to form an assembly of droplets, and this assembly of droplets results in scattering of light, and the pattern appears, the surface appears to be white. So this is what the very earliest observation on breadth figure, and people have started working on understanding the rate at which the breadth figure, the condensation happens onto the surface, and also the kinetics, the stages. So many parameters they were so fascinated while doing the controlled experiments. And during the early stages, what all the experimentalists focused is to maintain a very cold surface, very high humid water vapor, then there is a requirement of a carrier gas or a flow is required. So these three conditions, they always varied, and they try to focus on maintaining these conditions. And the other thing that varied to understand the breadth figure formation is the nature of substrate. It can be a glass, it can be a tin surface. In some of the earlier works where they try to condense the vapors of mercury, tin onto the surface of glass and so on. So the nature of substrate and the nature of the material that is being condensed is also varied and studied. The temperature of the gas, generally water vapor is used to study the condensation, but there are some instances where the molten metals or some solvents are attempted to understand the condensation process. It also requires to have a flow rate. The flow rate is required to have something called a pattern formation, And then the percentage saturation, if it is highly saturated, more amount of what is called droplets are formed at the initial stages, and so on. So they concluded that there are 4 successive regimes or stages in any droplet condensation onto this one. The first stage is the nucleation, which usually follows the exponential time kinetics of a to the power 1/3. The parameters A is a function of substrate temperature, the relative humidity, the flow rate, and so on. Generally, all the people observed that it is a function, 1/3 exponential function. Then they had something called the growth of the droplet. Once the nucleation is done, then there is a growth of droplet, which goes by generally by 2/3 of the exponential function. Then there is a third stage, which is the coalescence of the droplets, which is in tandem with the growth and nucleation. And what happens here is there is something called a force felt between the individual droplets across the condensing surface, and this force is the one which resists too much of condensation, formation of a bulk. Bigger size droplets make the droplets uniform and so on, and this force is a function of viscosity of the condensing droplet and so on. So this initial work is more focused on how these droplets are condensing onto the surface. But the very first report, which as far as I know came from the Steyer group, where they focused on, can we freeze the droplet or the imprints of the droplet onto the surface? Because the other surface, glass surface, you have to do something called, during the process of condensation, you have to do the observation. But the first work was to capture the imprints of this droplet formation onto the surface. For this, the group used something called paraffin oil. Paraffin oil at very low temperature almost is a soft material, and it is hydrophobic in nature. And when you try to condense the water droplets onto this hydrophobic thin layer, the hydrophilic water droplets tend to push away these hydrophobic oil droplets. So you can also think of the soft material is having some kind of a segmental motion, flexibility is there, so the molecules tend to align into hexagonal patterns. And surprisingly, unlike other glass surfaces in the earlier cases, they observed the formation of several islands, and these islands gradually started growing. And once the islands meet the boundary of the neighboring island, they coalesce, and you can clearly see the boundaries of the islands. The hexagonal patterns are not uniform at the grain boundaries. So this is what the first observation. So the observation is the islands are growing and they have the tendency to merge, but you can see the island's boundary even after the merging process is completed and so on. So this is one of the very earlier example on capturing the droplet condensation even after the droplet has evaporated. Now let's move on to the polymeric films, because paraffin, if you think from the hydrocarbons, the low molecular weight hydrocarbons are typically gases. Then we move on to slightly higher molecular hydrocarbons, becomes liquid. Then it becomes semi-solid, low melting liquid solids, and then we go on to high melting solids and so on. That's the polymers. So let's move on to what is the limit in which we can do, what are all the necessary conditions for us to make this kind of pattern formation onto the polymeric thin film. So first they thought that, okay, anyhow, we need to have some kind of a self-assembly once the water droplets is condensing onto the surface. So they thought of choosing a block copolymers, polystyrene block, polyparaphenylene is chosen, while the polystyrene is comparatively flexible. This polyparaphenylene is more of a rigid kind of a polymer. So they thought that this polystyrene, polyparaphenylene tend to form some kind of a aggregation into these kind of structures when they are allowed to exposed to the condensing water droplets. The one which is having a free mobility can move, and resulting in very robust formation of what is it called, breath figures. Now they used the solvents to dissolve these kind of polymers. Many organic solvents were used like THF, chloroform, and so on. And they found that the carbon disulfide gives more regular morphology compared to the other solvents. And the film thickness they used varied from 0.1 to 1 millimeter, and the thickness of film does not have much influence, rather than the depth of well varies as a function of thickness of film during the earlier studies. The flow rate and humidity controls the dimension of the pores or the size of the droplet that is condensing onto the system. So with this, they want to know that whether it is so essential to have this kind of aggregate. So they tried with simple polystyrene and the star branched polystyrene, and found that these kind of patterns are well obtained in case of the blocky polymer and star polymer, not in the case of a simple polystyrene, using their experimental conditions. And to have one more functionality to the breath figure patterns, they tried to mix or blend with poly 3-hexyl thiophene. Poly 3-hexyl thiophene is also a hydrophobic molecule. And this poly 3-hexyl thiophene, which they have taken, is of low molecular weight compared to the polystyrene block polyparaphenylene. So this rigid rod polymers along with the poly 3-hexyl thiophene also formed a very nice uniform hexagonal pattern, for which they showed that this pattern is of on very large surface area, which can be made on a very large surface area of 1 square millimeter and so on. And wherever you see the hexagonal pattern, and with very few places you can identify the defects. So this work was done in the early or mid 90s. And this polymer also showed as used or increase the high thickness, you can see that you can also see something beneath the first layer. You can see some more pattern formation at the next level and so on. The first thorough study on the difference between the solvent was done by Ogale and co-workers. What they did is to choose two different solvents, let's say benzene and chloroform. Both of them have almost the same enthalpy of evaporation. So they need same amount of energy to get into the gaseous form. Because you coat the polymer film in the presence of solvent, and then when you allow gas to flow onto the surface of the polymeric film, because of the flow, the vapors which is readily which is close to the surface of the polymer film is swiped away, and then new vapors replace from the surface of the thin film, and because of that evaporation happens, and this cools the surface, and this cools the surface. Since the surface is getting cooled, and if you pass a humid air, the humidity try to condense into regular hexagonal droplets. So in the case of benzene, they got a very small pores. In the case of chloroform, they got a very large size pores. The difference between benzene and chloroform is benzene has a very low density compared to chloroform, plus the rate at which the droplet forms in the case of benzene is much slower than the rate at which the droplet forms in the chloroform is. And because of that, there are bimodal distribution of the pores that is formed onto the chloroform. Here, the comparison is done at the 70% relative humidity in the case of benzene and chloroform. This work is further revisited very recently, where in all the cases, it is always told that you need to have some solvent which is not compatible with the water, because water is hydrophilic, and you choose a solvent which is hydrophobic in nature. And because of the difference in polarity, difference in visibility, there is a phase separation, and that allows the polymer to get organized into this kind of a mesh-like structures and so on. This was the earlier belief, earlier observation until this work. What the authors they have done is they have taken the same polystyrene, and they try to dissolve in THF and form a thin coat, and they try to dissolve in chloroform and form a thin coat. And when the amount of what is called flow rate is around 20 milligram, 30 milligram, and so on, when you vary the flow rate at a relative humidity of 70%, only the THF showed some kind of a droplet condensation and breath figure formation, whereas in the case of chloroform, there is no such pattern observed, except only in the case of 40 milligram per liter flow rate. The reason for the absence of any condensation onto the surface of chloroform is attributed because the chloroform is not comfortable to be miscible with water. So when the flow rate is very low or very high at very low relative humidity, the chloroform layer is consistently removed from the surface, but since the amount of water droplet present is very low, it finds it difficult to interact with the surface rich with chloroform to condense. And that's what the authors believe. They believe that the THF allows the water to readily settle onto their surface, and then slowly the water droplets evolve. So once the water enters into the surface or deposits onto the surface, the THF prefers to stay with the polymer, or the polymer doesn't like to leave the THF because it has to become highly concentrated solution. So there is always a natural tendency for any concentrated solution to be, any dilute solution to be in the dilute solution and so on. So the solvent is phase separated, even in the case of THF in the presence of water. The same experiment, when it is carried out at very high humidity of 90%, as observed earlier, the chloroform gives multimodal pore formation, whereas the THF showed more or less even distribution of this pores. The inference authors made was the following: you need to have an optimum flow rate, and the optimum flow rate is a function of the solvent polarity. The optimum flow rate is also a function of the viscosity that is present in the thin surface. So the viscosity is due to the solute, that's the polymer that is dissolved in the solvent, either it can be THF, chloroform, benzene, or whatever it is. So the flow rate is to be chosen, and that has to be chosen depending upon what kind of solvent and what kind of polymer you choose. And depending upon that, you can generate or you can control the morphology and the pore dimensions of the polymers. This is what the consolidated chart. When you have only THF, you have a very small pore size. And when you have only chloroform, you have slightly bigger pore size. But when you try to mix the chloroform and THF, then there is some kind of a three-component system where the polymer is there, chloroform is there, and THF is there, and there is a tandem reorganization of solvent. The rate at which the chloroform evaporates is different from the rate at which the THF evaporates in the mixed binary system, and so on. And it's kind of a tandem system where you generate different morphologies and different pore size. So coming to the effect of solvent, the density of solvent is also very important, because most of the time the breath figures are performed in a flat surface where you have, let's say, a thin film on to which the solvent molecule is distributed evenly. When the solvent molecule is heavier than the condensate, most often it is water droplet. If the solvent molecule is having higher density compared to the water droplet, the condensation of water droplet pushes the solvent molecule further down and creating a very deep or multiple layers of this breath figure formation or pattern formation. If the solvent molecule is lower in density compared to the condensate, the water droplet, then you always end up with a single what is called layer of this condensate. And this work has been thoroughly examined with the various solvents by Professor Mohan Srinivas Rao, and where he proved that by using the carbon disulfide and toluene, you can get two different patterns, and also the depth profiles also varies. Now come to the molecular weight dependencies on the pore size and the breath figure formation. The Peng group worked extensively on understanding the what is it called, pore formation as a function of molecular weight. If you take a very large molecular weight polymer, let's say 1,970,000 molecular weight of polystyrene, and compare with a very small molecular weight of polystyrene, let's say 30,000 molecular weight, kilogram per mole, what you find is the high molecular weight never forms any breath figure formation. There is no breath figure pattern seen onto the polymer which is of very high molecular weight. So there is a threshold molecular weight because you need to have some kind of freedom for the polymer to move and reorganize. So if the molecular weight is very large enough, the high molecular weight polymer finds it difficult to reorganize and form the pattern. Then if you take a very small molecular weight, the movement will be too fast, and then you will have a non-uniform or uncontrolled breath figure formation. So there is an optimal molecular weight requirement for making an uniform and also controlled pore size in the case of thin film breath figures. Now coming to the next point, most often we are of the belief till date, the belief is that if you have a polar end groups, that will facilitate the formation of the breath figure, and if there is absence of any polar groups, and it is very difficult to get a what is it called breath figure formation. But this particular group have deliberately avoided the use of polar end groups, and then they said that the viscosity of the medium or the chloroform viscosity of the solution is more important than the end groups. That's what they demonstrated by varying the molecular weight alone, and they have done with several concentrations, and even with very high concentration of the polymer, they find the pattern formation is not uniform, and the pore size becomes very small, and multimodal distributions came, and so on. And as a function of the relative humidity, if you increase the relative humidity, obviously the pore size is expected to be larger because you tend to have more amount of nearby droplets, coils, and so on. So this also has been done at 1% concentration of the polymer solution with from very low relative humidity to very large relative humidity. Now, to some extent, we got some idea about how to generate this kind of pattern formation onto the surface. So, is it possible to do some kind of chemistry, or is it possible to functionalize the inside of the pore, or it is possible to decorate the pores and so on? Is the question that has been taken one step ahead. So, one of the work that was attempted in the early days was to see if I can make uniform discs onto the thin film surface. So the Boyer and group, what they did was to first make a breath figure onto the surface of the glass using the polymer as shown here. This is the black copolymer, and you have this octyl side chain, octyloxy, and then this is a MEHPPV. Not MEHPP, it's an octyloxy polyphenylene, and then you have the styrene. These two are linked to diblock copolymer, and the R group is the one which is varied. The R group is the it's not varied, actually. It is the what is called growing chain end. This polymer is made out of the polystyrene is made out of the nitroxy mediated polymerization. That the R group is the free radical, the growing chain end, and so on. Okay, terminated with the, if you see the NMP method of polymerization, you see that you will know that the NMP will be locked into the chain end as a transition or in between state. Now, once you have this kind of a polymer, and this polymer is coated as a thin film, and allow this polymer to take the breath figure pattern, and then you do the UV curing in the presence of curing agent. And then the next step is a very interesting idea, that you take a scotch tape and then you keep it on the top of the thin film, and then peel off the scotch tape. And the scotch tape, if you see that these are all the weak links in the wells, and these are easily broken, and you remove those this one, then you wash the polymer, And the blue one is the one which is the aluminum that is coated, and you can see that you remove the aluminum discs and so on. So the photo-oxidized polymer is forming like a rigid substrate, and then you coat it the aluminum by deposition method, and then you peel off, then you generate something called aluminum cups and discs. Another approach to decorate the core is to see whether if I can put this gold nanoparticles like what it is shown here, where you take these gold nanoparticles, sorry, not gold nano, cadmium selenide nanoparticles, which are of dimension of a few nanometers. If you recollect, this dimension is of let's say few microns, and this is a few nanometers, and then try to decorate this inside lining by allowing this cadmium selenide nanoparticle to migrate from the bulk to the periphery by modulating the whatever the solvent conditions. So they have achieved this at this particular composition when you have 7% of polystyrene with the molecular weight of 78,000, and then you prepare 1% solution, and then you prepare this what is it called, cadmium selenide nanoparticle, which is of dimension 4 nanometer, and you mix in the ratio of usually they have done at various ratios, 5:1 to 12:1 and so on. At relative humidity of 80%, they try to generate these kind of cadmium selenide nanoparticles. You can see the fluorescence that is emanating from the rings, which is indicative of the deposition of these cadmium selenide nanoparticles onto the rim. And this is very interesting work carried out by the Han and co-workers. What they have done is they try to see, once you make a breath figure, is it the end of the experiment? Can't we still further modulate the pattern which is formed earlier and so on? So they cleverly designed a work where they took polystyrene of around 2 lakh molecular weight, and then they mixed with this poly 2-vinyl pyrrolidone of 11,000 molecular weight. The molecular weight of polystyrene is very large compared to the molecular weight of the polyvinyl pyrrolidone, which means that the mobility of P2VP is slightly higher compared to the polystyrene. Plus, the poly 2-vinyl pyrrolidone is slightly polar in nature compared to polystyrene. They mixed these two polymers in the ratio of 5:1, then allowed to make a breath figure. And once the breath figure is made, the first one is as prepared breath figure. And then what they have done is they allowed this particular patterned surface to solvent. So for example, if you give exposed to ethyl alcohol or so on, this ethyl alcohol try to swell the poly 2-vinyl pyrrolidone to a larger extent compared to polystyrene. Polystyrene is not soluble in what is called ethyl alcohol. So in that case, the polyvinyl pyrrolidone swells. It don't dissolve, it swells in the ethyl alcohol. And the swelling results in the evolution of pillar. As you can see, if you increase the exposure time of this ethyl alcohol into the already prepared breath figure, you get these kind of protrusions coming out of the place where there were initially wells here. And these are all due to the swelling of poly 2-vinyl pyrrolidone. So once you get this swelling done, can you make it to go back? Yes, you remove by heating them at around 60 degrees for 1 hour and 3 hours and so on. So you get back the same, whatever the polymer that pattern that was earlier. And similarly, the same work was done with another solvent, the carbon disulfide. The carbon disulfide has a different characteristics compared to the ethyl alcohol and so on. The carbon disulfide tend to push the polystyrene, and then you get some kind of a ring development because of the exposure of carbon disulfide. Same experiment is done by exposing carbon disulfide, and at each time interval you see how the surface is evolving as a function of this exposure time to carbon disulfide. And finally, if you get rid of the carbon disulfide by exposing it to chloroform vapors and so on, then what happens is you get back the original pattern which you started with. So this way they are able to modulate the surface in Z direction vertically. They can pull something like a nanopillars from micro pillars to micro wells. The next work is on getting elliptical pores. Is it the only problem that we always get what is called circular pores in Bretiger pattern? Is it possible to get an elliptical pores? So here also the experiment is done by carefully designing the experimental setup. So what they did is they took this dodecane thiol capped gold nanoparticles, and they have taken this one in toluene, and then they allowed the air to flow at an angle of 15 degrees Celsius instead of what is it called perpendicular. They just slightly tilted the airflow and varied the rate at which the what is it called airflow is done, and by modulating the angle and also by modulating the airflow, they are able to show that it is possible to get something called an elliptical pattern. And this pattern is because as the water takes an elliptical form because of the airflow, it pushes away the polymer and gets these kind of patterns onto the surface. Now the another group, what they wanted to do is why to restrict the formation of this what is it called pattern by only having the airflow. I would like to they would like to make something called variable pores by doing something called mechanical modulation or mechanical stretching. So for that, what they chose is to take something called caprolactone. So the polymer caprolactone is known to show some kind of elastic behavior, and they use this polymer in the presence of the amphiphilic polymer of this N-octyl and N-carboxylic acrylamides, and they use this amphiphilic polymer to blend in various ratios and bring in the elasticity, and they prepared the breath figure without disturbing the what is it called surface or the thin film. And after that, they could stretch the polymer slowly. The polymer once stretched, they could give from this kind of a circular to this kind of a elongated or ellipsoidal, and by changing the direction in which the stretching is applied, they could generate several varieties of what is it called pore dimensions, dimensions like hexagonal, square, rectangular, triangular. By twisting into angles, they got triangular and so on. So this is another interesting approach in which the thin film is transformed into varieties of morphologies. The another approach done by Shen and group is to allow these nanoparticles to form decorated rings. And if you see this is the silica nanoparticles that takes the what they call positions of the ring, and the silica particles are fluorescent labeled, and they are allowed to, the particles are of very small dimensions compared to the dimensions of the pore. And these polymers are, the particles are chosen in such a way that the concentrations are very low enough to occupy only the rings and avoid the other places. And if you carefully see the mechanism proposed by them, during the process of evaporation, the particles migrate from somewhere in the interior towards the ring, which means that the particles have some kind of the surface functional groups that are attracted towards the hydrophilic environment. So it is the silica particle with a porous silica particle with some fluorophore inside it to have an optical or fluorescence image taken at later stage. To do chemistry onto a very small scale is also very fascinating. This asymmetrical titanium dioxide microparticles. These asymmetric particles are of immense interest for physicists for various applications such as photonic band gap materials and so on. But preparation of these asymmetric particles is not so easy. This particular group, what they did is to try to make the nanoparticle inside or microparticle inside the well by having these kind of precursors to the nanoparticles blended along with the whatever polymer thin film you make. So they took this titanium chloride, polystyrene and chloroform in such an optimized ratio. They allowed this water droplet to condense onto the surface. Since this titanium chloride is highly reactive to the water, it reacts and forms titanium oxide, and this titanium oxide, since it is confined to this particular water droplets as a nano container or a micro container, you generate these kind of what is it called particles onto the surface. And due to the evaporation, initially the titanium dioxide will be spherical, and due to the evaporation slowly it flattens out. And they have shown that this is as prepared film taken from the what is called vertical angle, perpendicular angle, and now this is on the side view of this titanium dioxide hemispherical microparticles. And these particles are peeled off in a scotch tape, and you can see the hemispherical region here and the disc region here. So they have proved that it is possible to generate what is called unsymmetrical microparticles onto the surface in a very simple approach. And this is the what is an image of the collected particles. Even more interesting work is done by other group where they wanted to blend 3 different polymers, and 3 different polymers are chosen in such way that all 3 are mutually incompatible. For example, polystyrene and polyethylene glycol methacrylate and a fluorinated homopolymer. This is pentafluorinated polystyrene is taken, and these 3 polymers are orthogonally means they are immiscible among themselves, and they have taken in such a ratio that what is it called, they form during the process of the breath figure formation. They align in such way that you have one particular type of polymer to be placed wherever you want. In this case, what they have done is, in the perfluoropolymer is of low molecular weight, and this is a diblock copolymer, and this diblock copolymer takes the major skeleton, whereas this perfluoropolymer which is done something called thiol click at the para position by some.
Can you be a bit louder or closer?
Okay. This perfluoropolymer at the para position is surface modified by doing some thiol click reactions and with the hydrophilic groups, which they have chosen some kind of a sensing element for what is it called, conavalin, some drug molecule, or it is some biomolecule, which I am not very sure about it. And then they try to see whether the 3 polymers are placed at the place they wanted to. So when they have done something called confocal Raman chooses or maps the particular frequency on the onto the surface by doing something called surface scanning, and these maps are reconstructed. Sorry, this what the picture, confocal Raman picture, is a reconstructed picture from the independent wavelength that were analyzed over the what is it called, surface. What they have found is this perfluoro is the one which is taking the rim inside the pore, whereas the other one is taking the other 2 polymers are taking the skeleton. And what they did is they tried to do something called functionalization of this perfluoro group, which is present onto the rim, by doing something called click chemistry in the presence of, after forming the breath figure, they did the click chemistry onto the surface. And this is fluorescent in nature, and they could also get the fluorescent image of this molecule on the surface. Now we made unsymmetric particles, shown that the unsymmetric particles can be made in these micro wells of this titanium chloride in the presence of water from titanium dioxide hemispherical particles. Similarly, people are curious whether polymerization can be done inside the system. So they first made the breath figure. Here what they have taken is, they have taken polystyrene block poly 4-vinyl pyridine. And this 4-vinyl pyridine, that nitrogen is a hydrogen bonding acceptor. So what they did is, when you make this kind of a block copolymer as the polymeric thin film, you align this vinyl pyridine in such a way that it is exposed close to the core of the microville. And once you expose or align this by swelling, even if at the time of formation of breath figure, if it is not aligned, you can always use the ethyl alcohol vapors to pull these molecules to come closer to the interior of the microvilles. Once you align this vinyl pyridine molecule to a larger extent to the interior of the microvilles, you allow these molecules to be hydrogen bonded with small molecules such as this pyrrole, aniline, and thiophene, and so on, thiophene carboxylic acid. So this forms the monomer. This allows the monomer to be aligned inside the cavity. And once the monomers are aligned inside the cavity, you do something called chemical oxidative polymerization and generate a polymer within the microvilles. So I think I have shown that the breath figure technique has evolved over a period of last, let's say, 30 years and so. And now people have mastered the ability to surface modify, to do carry-out reactions, and to generate patterns as what they desire. And this is a very simple technique. It can be done in a very simple setup, which is having a lot of potential. Thank you.
Thank you very much, Dr. Ramkumar. This particular topic is close to our hearts because this is the work that we have been working on, collaborating on for the last few years, and
Yes.
Understood the physics of the presence of constraints in the substrate and how it affects the patterns. Before I go on to the Q&A, I have a couple of announcements for those of you, for the participants. The link to the feedback form, which is essential for your certificates, have been posted in the comments on Zoom. And for those of you on YouTube, I think the link is too long. So we are monitoring who's on YouTube, and you will be sent a link there. So please bear with us until then, because we are keeping a track of who's live on the session. So that, and those of you on Zoom, please check the comments. The link is already there. Thank you. So let me ask you a couple of questions that have been raised, Dr. Ram. Dr. Kamani, again, I think it's the same question that he was trying to ask from last time, from a doctor's perspective or from the perspective of a common man. Using these techniques, can you think of how to modify a surface so that you can make it, you can tailor-make it for a COVID patient, non-COVID patient, a COVID patient doctor kind of a scenario? Do you have any ideas on that?
Yes, we have proposed and we are thinking to do this kind of work. What you can do is, suppose if you have a, let us say, a polymer material which is of a very large dimension, you expose those material to solvent vapors to just allow them to swell. For example, you can expose to chloroform, in the case of polymeric fabric, and then you allow this fabric to condense onto the droplet at a very low humidity or a controlled humidity. You have to do. Why? Because you can also fine tune the pore size of this polymer, thereby you generate some kind of membrane. If you can achieve a very small pore size, this can be used as a kind of an air filter, a breathable membrane, which can be used or maybe useful for one-time or two-time use. Since it is polymeric material, it can be washed, it can be exposed to UV, kill all the surface adhering virus particles, and then reuse several times. That's what I believe, but I don't know whether it can be doable in such a large scale. Breath figure has been demonstrated to be done meter scale, but I don't know whether it can be done at this juncture.
I think COVID, unless all of us go back to our laboratories without the lockdown, answering these questions is going to be a bit tricky without actually doing the experiments. Everything else is going to be heuristic. Diliraj Upadhyay from, this is a comment from the YouTube. How will adhesion of a solution vary with the deposition method?
For example, in the case of spin coating, you get very, very thin uniform thin film, whatever it is, in the case of spin coating, because the time that is available for this particular solution to interact with the substrate is significantly lower, and there is also a shear force involved on the during the process of thin coating or film coating. So the thin film what you obtained in the case of a spin coating completely differs from the thin film that is obtained by other technique like drop cast. In the case of drop cast, what happens is if you don't hit at the viscosity at which you get an uniform thin film, you always end up in something called a coffee ring effect. So that's the problem with the what they call drop casting method. So the same polymeric solution by two different technique will give two different film thickness, and that's because of the nature in which you make the thin film.
Dr. Tapti, who is our panelist and the speaker tomorrow, asks, are the polystyrene beads in water charged? If so, what is the nature of charge? What will be the likely configuration of their aggregation and water?
The polystyrene, whatever are most studied in almost all the works, is nowadays a simple polystyrene without any charge. But your question is very interesting. Like if you have a, let's say, polystyrene sulfonic acid, polystyrene sulfonate, where you can have this kind of charged system as a sodium salt. And the moment you have charged system, the charged system will tend to align along with the water domains. And the pattern formed might have all the sulfonic acid that is facing the core, facing the microvales.
Thank you. Tejas, did you have a question?
Oh yes, oh yes.
Yeah, please go ahead. This is Tejas Katta, your student Ram.
Hello, Dr. Ram.
Hi, Tejas. Yes.
Hey, good to see you again. So I was listening to your talk, and I was paying attention to the when you said that you could make impressions of drops on the surface.
Yes.
So I was wondering about the possibility of, you make a drop and you have some sort of a crystallization happening inside the droplet.
So the droplet is not a pure water.
No, it can be, but it may be some solution that could crystallize very easily also.
Okay, fine.
Such scenarios, I'm just thinking aloud about, a fascinating scenario. That's it.
I didn't follow the question. Is you want to know what happens if you have some crystallizable material in the condensate?
Yep.
Okay. What is known in the literature is people have tried to mix some of the inorganic salts along with the, what is it called, the substrate, because it is not possible to carry water vapor with the salt. You should already have those kind of inorganic salts onto the substrate. And they try to mix some small amount of sodium chloride, some small amount of calcium chloride into the blend and try to see what influences. In one work, which I have not shown here, what they have done is they have obtained this kind of hexagonal pattern of these materials. Say, for example, they have done in calcium chloride. So calcium chloride itself took the, what is it called, hexagonal skeleton. So it formed the frame when the water condensed. So that was really surprising. Usually calcium chloride dissolves in water, but since the water is slowly evaporating, it pushes off the calcium chloride to form the outer skeleton. So that's completely different work. It's not related to breadth figure, but the solidification results in some kind of structure obtained very similar to the breadth figure.
Right. So one more quick question is that aren't these ideas the underlying basis for, the materials like DuPont and other companies they prepare, right?
I have no idea about the companies. Usually what they do is they try to convert the polymer into a technology and from the technology to the product. So it doesn't matter what polymer they choose. Finally, they want to convert it into a sellable product. So I have no idea about what the industry would do with this kind of morphology modified materials. I have no idea.
Right. Thank you, Dr. Ram.
So there is a add-on question to this from Otushi, again one of our panelists. She asked, is it because calcium chloride is highly hydrophilic?
Calcium chloride, no. So what happens is, in that particular work, the skeleton, they were not explaining about the breath figure formation or something like that. They are saying that the water that is trying to evaporate is pushing out the calcium chloride to the edges, and because of some other effect not related to breath figure formation, it generates this kind of a hexagonal skeleton. I don't know whether it's not related to breath figure. It's not related to breath figure.
Not related to breath figure. No, related to breath figure. Professor Sujata Tarafdar, again our panelist from tomorrow, asks, what are the applications of these 3D patterns?
Applications of these
3D patterns, the breath figures, the 3D.
No, the 3D patterns. They say that you vary the density of the solvent that is used to cast the film. That is responsible to generate the 3D patterns. That's the first thing. The 3D pattern, in the sense I am mentioning about, you have multiple levels of this water condensate. Now, the application, probably, if you can control where the 3D patterns forms the grooves and so on, you can use a photonic band gap material by channeling out and by putting relevant mass.
Hear you really. I think you need to be a bit closer to the mic. But I think I might add that there are a lot of applications in microfluidic devices, in inserts, templating, etc., etc. There is one non-breath figure question. How do the micro droplets affect atmosphere during the COVID situation? This is from Govind Narayan Dute.
How the micro droplet
effect in the atmosphere affect COVID situation?
This question, I think previous speaker also addressed. The rate of evaporation is a function of many parameters, including what is the ambient temperature, what is the and what is the position of the droplet, how much concentrated the droplet is.
That's right. The other thing is the smaller droplets will travel a longer distance, whereas the larger droplets fall quickly. Dr. Tapti wants to ask you something directly. Dr. Tapti, please go ahead. Tapti?
Hello?
Okay. Before she comes in, Shrija from here is asking you why the thickness of optical, electrical, and other thin films are chosen from different ranges.
No. It is not chosen. Actually, it is the property that is exhibited. Because of the wavelength limitation, usually, see, for example, if you have this Brax mirror, you have two different layers, and the difference in what is called the dielectric of the layer 1 and layer 2 goes to the order of magnitude 500, and it's a lambda by 4 nanometers. That's what I remember. I am not sure. So that scales up with the wavelength of the light that you explore. In the case of electrical, you work on the rate at which the electrons move from one terminal to other terminal across the thin film. You don't worry about the electrons going through the thin film. So you want to say you have a layer 1 like this, and you have another layer. You worry about how the electron. So the mobility of electron is limited to a very smaller dimension compared to the properties that we worry for the wave light.
Can you be closer to the mic again? Tapti, if you're ready, can you ask the question?
Yes. Can I ask?
Yes,
yeah, please.
Can you hear me?
Yes.
Yeah. In one of your slides, you showed that the polymer had dissolved in it silicon dioxide or one of constituents, which kind of rose up and arranged themselves around the rim in the impression that was formed.
Yes.
I was thinking that is it possible to have your water droplets containing, say, a very low concentration of some soluble salt, and then allow it to deposit as breath figures, and then as the droplet evaporates, to have a coffee ring effect, which will generally coat the interface of the impression made on the polymer. I mean, instead of it rising from the polymer, it comes from the droplet due to the droplet evaporation.
Yes, actually, what we do in this kind of breath figure generation is to allow the water vapor to condense onto the cold surface or onto the surface. It is not possible to have the water vapor mixed with some kind of an inorganic salts or whatever salts to. It is not possible because it's in vapor form. So the only way we have is to have the salts already present in the thin film substance, the substrate. And if these inorganic salts are hydrophilic in nature, they tend to move very closer towards the hydro water.
I would like to kind of disagree and say that you can use a saline solution as the water droplet, and that ends up decorating the inside of your breath figure. This is what we try doing when you try to get a hierarchical roughness.
Yes, but the control is not
I mean, how you control it is
concentration of the whatever you have will be very. It's
no,
not
but that's
controlled.
definitely a known path for nano decoration of the pits that form in a breath figure. So yes, in principle, yes, I would say that that is in principle true. Dr. Kamani again has a question.
Thank you.
What are the yeah? Thanks, Dr. Dr. Kamani wants to know what are the applications of biodegradable polymers.
Biodegradable polymers in general, by definition itself, it's used where you need not worry about the degradation, polluting the environment. You need not worry about discarding at a, what is it called, place where you have to take care of whether it will prevent the percolation of water and so on. So the biodegradable polymer has more of environmental application rather than what is it called, it's more focused on environmental sustainability and so on. To bring in the same property of the synthetic polymers to the biodegradable polymer, you have to modify the biodegradable polymers, and that actually spoils the biodegradability of the polymer itself. So it's kind of you want to bring in the polymers which are functional polymers by modifying the biodegradable polymer, and that will make the biodegradable polymer to lose its characteristic features of biodegradability. So I think biodegradable polymer has very limited applications. Maybe blends might work. I don't know. I have not explored on the blends. Modification of biodegradable polymers always results in a non-biodegradable, or it gives the byproduct which are not good for the environment.
Wonderful. I think with that, we come to the close of the formal sessions. Thank you very much. And to all of you, I request you to log in tomorrow at the same time on Zoom by about 9:50 so that we have some time. Today, we have had some issues on the live streaming because it worked either on Facebook or on YouTube, and it gave us some problem. But tomorrow, please be back because it's going to be a very interesting session on the patterns that are found when a droplet actually dries and how to interpret them. So see you all tomorrow. Please log in by 9:50 and let us know if there is any feedback. Thank you, Dr. Ram, and thank you, Dr. Dasirai. Thank you, everyone.